Now, if only things were that simple in DSP, unfortunately, a lot of our waveforms are not real and infinite length. They're in general going to be complex and finite length. And before we get there, let's tackle what we're going to do just with complex and infinite length signals. And we're going to break those up into something called a conjugate symmetric part, that's CS, plus a conjugate antisymmetric part, where the conjugate symmetric is going to be like even. So when you see the conjugate symmetric, think that symmetry is like an even symmetry, and when you see conjugate antisymmetric, think an odd signal. And the formula to extract the conjugate symmetric portion of a signal looks therefore almost like the formula to extract the even part, except instead of, whoops, excuse me, except instead of adding your flip signal, you add your conjugate of your flip signal. So that means the conjugate, which means in rectangular coordinates, 2 plus j6, conjugate is 2 minus j6, or in polar coordinates, 3 at an angle of 20 degrees. Conjugate would be 3 at an angle of minus 20 degrees. In the complex plane, we're just flipping it vertically. So let me give an example of this. So it's going to be infinite lengths. We're going to have a dot, dot, dot to show that it's all zeros out here. And then we get to a 1 plus j. So I'll make this real. 1 minus j. 0, 0, dot, dot, dot. All right. So it's conjugate symmetric because this is its middle point. I actually should have defined that in the same colors. This is an inherent part of the sequence. All right, so these units are complex conjugates of each other. The real part is even, and the imaginary part is odd, so the entire thing is conjugate symmetric, which is what I want you to think of is like even. And zeros are always both conjugate symmetric partners and conjugate antisymmetric partners. So you can kind of guess how the conjugate antisymmetric part goes. It's like the complex version of being odd. It's 1/2 times the original signal minus now the conjugate of the, let me make that minus clearer, the conjugate of the flip signal. So just as an example, if we had dot, 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 0, 1 minus j here, 0. By the way, odd signals, they always have to have a 0 at the center point. And my question is, what does this have to be? And the answer is, for it to work, it's got to be the conjugate antisymmetric portion of this partner of this one, which means that the real part has to be odd And now the imaginary part has to be even. So it's odd, and the imaginary part is even. Just like here, the real part was the same and the imaginary part was opposite signed. Here, the real part is opposite signed. The imaginary part is same signed.
Sir, I have a quick question. For the conjugate antisymmetric part, the
Yeah.
blank you just filled out, can you go over that again?
Sure. So for conjugate symmetric, which you know is not the question you asked, the real parts stay the same as you flip them around the horizontal axis. The imaginary parts change sign. For the conjugate antisymmetric parts, the real part changes sign, and the imaginary part's sign stays the same.
Thank you, sir.
Just as an example of how to do this, now I'm going to keep it at that. That's the simplest. That's simple and it's accurate.